Here's a thought that should genuinely mess with you a little. The planet you're standing on right now, the one that's 70% covered in water, the blue marble, the pale blue dot, the ocean world, that planet, by all the laws of how it formed, should be bone dry, like desert dry, drier than the moon dry. Earth's oceans physically should not exist. And yet you've got more than 300 million cubic miles of the stuff sloshing around, and nobody handed it to you with a receipt. So somebody's got some explaining to do. Okay, so if this kind of thing scratches an itch in your brain, do yourself a favor and hit subscribe. We post these every single week. Ring the bell if you're feeling fancy, and I promise we'll keep finding ways to make you stare at a glass of water like it personally betrayed you. Cool? Cool. Let me explain why your oceans are basically a crime scene. Let's go back, way back. Picture this. The year is roughly 4.5 billion years ago, and there is no Earth yet. There's just the sun, freshly switched on, a screaming infant of a star, and around it a flat, spinning disk of gas and dust and rubble. Astronomers call it the protoplanetary disk, which is a fancy way of saying a giant cosmic mixing bowl. And in that bowl, everything is sorted by heat. Close to the sun, it's an oven. Far from the sun, it's a freezer. And that one detail, how close you are to the fire, decides everything about what a planet is made of. Now here's the concept you need to lock into your head, because the entire mystery hangs off it. It's called the frost line. Sometimes people call it the snow line. Basically, it's an invisible boundary out in the disk, a certain distance from the sun, and it marks the spot where it finally gets cold enough for water to freeze into ice and stick around as a solid. Inside that line, closer to the sun, where Earth was forming, it's too hot, way too hot. Any water out there isn't ice, it's vapor, and that vapor gets blasted and shoved around by the young sun's radiation and the solar wind like a leaf in a hurricane. It doesn't condense, it doesn't settle, it doesn't get built into the rock. And that's the problem. That's the whole problem in one sentence. Earth formed inside the frost line. Earth formed in the dry zone. The chunks of rock and metal that smashed together to build this planet, those building blocks, planetesimals, if you want the word, they came together in a region that was too toasty for water to be part of the recipe. So the Earth that assembled itself out of that material should have come out of the oven as a dry, rocky, baked little world, with basically no water locked inside it at all. A rock. A big, warm rock. You with me? Because this is the contradiction. You've got a planet that on paper was born dry, in the dry zone, too close to the sun for water to survive. And yet that exact same planet is the wettest world we know of in the entire universe so far. 70% of its surface is ocean. There is so much water here that we named the place after dirt and then covered most of the dirt in water anyway. Something doesn't add up. The water arrived later, from somewhere, and finding out where is one of the great detective stories in all of science. So let's actually do the detective work. Let's follow the water. But before we go suspect hunting, you have to understand just how violent baby Earth's childhood actually was, because it makes the water question even crazier. Forming a planet is not a gentle process. It is not dust politely clumping into a ball. It is the most demolition derby thing imaginable. You start with dust grains sticking together by static cling, basically, into little pebbles. Pebbles bump into pebbles and make boulders. Boulders, with enough gravity, start pulling in other boulders, and now you've got mountain-sized chunks, and those chunks slam into each other at thousands of miles an hour. Every collision is a catastrophe. Every merger is a wreck. And slowly, over millions of years, out of all that wreckage, you get a few big winners that have swept up everything in their path. One of those winners was the Proto-Earth, and just when you'd think things were starting to settle down, the single most dramatic event in the planet's entire history shows up to ruin the day. Let me set the scene for you. The early Earth is mostly formed, a molten, glowing, hellish ball, and it is not alone. Sharing roughly the same orbit is another world, another planet. We call it Theia, named after a Greek goddess, specifically the mother of the moon goddess, which, spoiler, is the most appropriate name in the history of names. Theia is not small. Theia is about the size of Mars, a whole separate planet, roughly half the diameter of Earth, on a collision course. And here's the crazy part. They hit. Not a graze, not a fender bender, a full planet-on-planet, world-ending collision. This is the giant impact hypothesis, and it is the leading explanation for where the moon came from. Theia, a Mars-sized planet, slammed into the young Earth at a glancing angle with an energy that is honestly hard to put into words. The impact released enough energy to vaporize rock. It liquefied the outer Earth into a global ocean of magma. It blasted a colossal cloud of debris, chunks of Earth, chunks of Theia, all melted and mixed together, out into space, where it formed a glowing ring around the planet. And over time, that ring of vaporized rock cooled and clumped and pulled itself together into the moon. That's right, the thing you look at night, the thing that gives you tides and eclipses and werewolf movies, is the cooled down splatter from the worst day this planet ever had. Now think about what that means for water. A collision that powerful was effectively a planetary reset. It was a do-over button slammed so hard it cracked the case. The energy of the Theia impact was more than enough to boil off and blast away pretty much any water that might have somehow clung to the early Earth. It should have sterilized everything. Anything volatile, anything that evaporates easily, water included, would have been cooked off into space or roasted out of the rock. So even if, by some miracle, baby Earth had managed to hold on to a little bit of water, despite forming in the dry zone, the Theia impact comes along and basically says, nope, and wipes the slate clean. So now the mystery isn't just hard, it's doubled. Earth formed dry because it was inside the frost line. And then, in case that wasn't dry enough, it got hit by a Mars-sized planet that should have cooked off whatever moisture was left. 2 strikes. By rights, this planet should be a parched, cratered, lifeless husk, more like Mercury than the world you know. And yet, the oceans are right there. So the water didn't just need to arrive, it needed to arrive after the chaos, after Theia, after the magma ocean. The water that fills your seas today got delivered to a planet that had every reason to be a desert, and it got delivered late, like a cosmic package showing up long after you'd given up waiting for it. The big question, the question that's launched billion-dollar space missions and careers and arguments that get genuinely heated at conferences, is who's the delivery driver? Let me introduce the first suspect, and honestly, it's the obvious one. It's the suspect everybody points to first, the one in every old documentary, the one that just feels right. Comets. Think about what a comet actually is. It's a dirty snowball, a chunk of ice and dust and frozen gas that formed way, way out in the cold outer reaches of the solar system, far beyond the frost line, out where water as ice is just a normal, everyday material. Comets are basically wandering ice mountains, and every now and then gravity nudges one of them, and it comes screaming in toward the sun on a long, looping orbit, growing that glowing tail as the ice boils off. It's poetry. Picture this. The early solar system is a shooting gallery, and these icy comets are raining in from the outer dark, smacking into the inner planets, and each one is delivering a payload of water to a thirsty young Earth. It's clean, it's elegant, it makes a great story. Comets bring the water, case closed, roll credits. Except, and you knew there was an except coming, when scientists actually went and checked, the story fell apart. And this is where it gets really good, because we didn't just guess. We chased a comet down across the solar system and stuck a probe on it. Let me tell you about a spacecraft called Rosetta. This was a mission by the European Space Agency, and it was an absolute beast of an engineering achievement. Rosetta launched back in 2004, and then it spent 10 years, chasing down a single comet, looping around the inner solar system, using gravity assist from planets like a cosmic slingshot, building up speed until finally in 2014 it caught up with its target. That target had a name only a scientist could love, Comet 67P, full name 67P/Churyumov-Gerasimenko, named after the two astronomers who discovered it. A lumpy, rubber duck-shaped chunk of ice and rock a couple of miles across, tumbling through space. And Rosetta didn't just fly past it. Rosetta went into orbit around it, orbiting a comet, which had never been done. And it even dropped a little lander called Philae down onto the surface. We landed on a comet. Sit with that for a second. We chased an icy mountain across the solar system for a decade and then gently set a robot down on top of it. Now why go to all that trouble? Why spend 10 years and all that money to sniff one comet? Because of a beautiful little trick of chemistry, a kind of fingerprint that water carries with it. And this is the key to the whole case, so let me explain it, because once you get this, the entire mystery snaps into focus. Not all water is exactly the same. Water is made of hydrogen and oxygen, H2O, you know the formula. But hydrogen comes in more than one variety. Most hydrogen is just a single proton with an electron buzzing around it, the lightweight standard model. But a small fraction of hydrogen atoms are a heavier version called deuterium. Deuterium is hydrogen with a little extra weight in the nucleus. It's got a neutron tagging along with the proton, basically doubling the weight of that atom. And when you make water using deuterium instead of regular hydrogen, you get what's called heavy water. It's still water. It still looks like water, behaves mostly like water, but it weighs more. And here's the genius part. The ratio of heavy water to normal water, the deuterium to hydrogen ratio, the D to H ratio if you want to sound smart at parties, that ratio acts like a barcode, like an isotopic fingerprint. Water from different places in the solar system, water that formed under different temperatures and conditions, ends up with different amounts of that heavy deuterium baked in. So if you measure the D to H ratio of Earth's ocean water, you get a specific number, a specific fingerprint. And then if you go measure the D to H ratio of some other source of water, a comet say, and the fingerprints match, congratulations, you found a candidate for the delivery driver. If the fingerprints don't match, that source is off the suspect list. It's that clean. It's chemistry as detective work. So that's exactly why we sent Rosetta. We went all that way to read Comet 67P's water barcode and check it against Earth's. We wanted to know, once and for all, does comet water match ocean water? Drum roll. In 2014, Rosetta sampled the water vapor coming off Comet 67P, measured its deuterium to hydrogen ratio, and the answer came back. And the answer was, no, not even close. The water on Comet 67P was about 3 times too heavy compared to Earth's water, 3 times the deuterium ratio. The fingerprints didn't just fail to match, they were wildly, dramatically off. This comet's water was a totally different flavor from the water in your oceans. And that basically ruled comets out as the main source. Now, fair's fair. 67P is one comet, and comets do vary a bit from one to the next. A few other comets have measured closer to Earth's value. But 67P was a gut punch to the comet theory, because it was supposed to be a pretty typical example of a certain class of comets, and its water was completely wrong. When you stack up the measurements from a whole bunch of comets, the average comet water is just too heavy, too rich in deuterium to explain Earth's oceans. The numbers don't work. You can't fill the oceans with a fleet of comets when most of them are carrying the wrong kind of water. The obvious suspect, the dirty snowball, the star of every old space documentary, turns out it's got an alibi. The water on the comets is not the water in your seas. So, back to square one, sort of. The most intuitive answer is wrong, or at least mostly wrong. The comets didn't do it, or at least they didn't do most of it, which means the real delivery driver is somebody less glamorous. And this is where the case takes a turn toward an unlikely hero, the suspect nobody expected, the boring-looking one in the back of the lineup. Now, Let me introduce you to the asteroids. When you hear the word asteroid, what do you picture? Probably a dry, gray, cratered rock, a dead lump of stone tumbling through the void, a planet killer from a disaster movie. And yeah, a lot of asteroids are pretty much exactly that. Dry, rocky, lifeless chunks. But here's the thing the movies never tell you. Not all asteroids are dry. Some asteroids are wet. Some asteroids are, chemically speaking, soggy. And those wet asteroids might just be the heroes of this entire story. Let me explain how an asteroid can be wet, because it's not like there are little oceans on them. The water in these asteroids isn't sitting around in puddles. It's locked up inside the minerals themselves. There's a whole class of rocks called hydrated minerals, clays basically, and other water-bearing minerals, where water molecules, or the chemical pieces of water, are chemically bound right into the crystal structure of the rock. The water is part of the stone. You could hold a chunk of this stuff and it'd feel like a dry rock in your hand, but heat it up and water would literally bake out of it, because the water was hiding inside the mineral all along. This is the key idea. You can carry water across the solar system without carrying ice, by smuggling it inside the rock itself, baked into the minerals. And there's a specific class of these wet rocks that scientists get really excited about. They're called carbonaceous chondrites. Don't let the name scare you off. It just means a primitive, carbon-rich type of meteorite, the oldest, most unprocessed leftover material from the very birth of the solar system. These are basically time capsules. They formed early, out past the frost line or near it, where there was water available, and they locked that water away inside their minerals, and they've been carrying it ever since. And when scientists get their hands on a piece of carbonaceous chondrite, and we have, plenty have fallen to Earth as meteorites, they can do the same trick they did with the comet. They can measure the water's deuterium to hydrogen ratio. They can read the barcode. And now we get the payoff. When you measure the water locked inside these carbonaceous chondrite asteroids, the deuterium to hydrogen ratio is a near perfect match for Earth's ocean water. The barcode lines up. The fingerprint fits. Where the comets were 3 times too heavy, way off, these wet asteroids are right on the money. Their water and your ocean water are, chemically, the same flavor, same recipe, same source. That, right there, is the smoking gun. The water in your oceans almost certainly came from wet, water-bearing asteroids, specifically the carbonaceous primitive ones that formed out where water was available and then got flung into the inner solar system, smashing into the early Earth and unloading their hidden cargo of water baked into their rocks. Isn't that a beautiful twist? The glamorous suspect, the comet, the dirty snowball with the gorgeous glowing tail, turns out to be innocent. And the unsung hero, the boring gray rock you'd never look at twice, the asteroid, that's the one that delivered the seas. Turns out the thing that gave you the ocean wasn't a poetic ice mountain blazing across the sky. It was a soggy gray rock that smelled, frankly, kind of like wet dirt. Which just goes to show, the most important deliveries often come in the ugliest packaging. But hold on, because we have to deal with the timing problem again. And this is where it gets even more clever. Remember Theia. Remember that the giant impact should have cooked off all the water and reset the planet. So if the wet asteroids delivered Earth's water, when did they do it? If they delivered it before Theia hit, the impact would have just boiled it all off again, and we'd be right back to having a dry planet. The answer is something scientists call the late veneer. And it's exactly what it sounds like. After the big violent chaos was mostly over, after Theia had hit and the moon had formed and the magma ocean had started to cool, there was a final, lighter rain of material onto the young Earth. A late arriving coating, a veneer, of leftover stuff from the outer parts of the solar system, including a healthy helping of those water-rich carbonaceous asteroids. So the wettest deliveries came late, after the planet had calmed down enough to actually hold on to them. The water showed up to the party after the bouncer had stopped throwing everything out. The timing finally works. Dry planet, giant impact, things cool down, and then, only then, the The wet rocks come raining in and bring the water that's going to become your oceans. The package arrives after the house has stopped being on fire. Now, I want you to really appreciate how much water we're talking about, because the scale of it is genuinely hard to wrap your head around. We tend to think of the ocean as this thin film on the surface, and in a way it is. Compared to the whole planet, the ocean is barely a wet sheen, like the dampness on a freshly washed apple. But in human terms, it's almost incomprehensible. There's something like 330 million cubic miles of water in Earth's oceans. The average depth of the ocean is over 2 miles. There are trenches that go down nearly 7 miles, deep enough to swallow Mount Everest with room to spare. And all of that, every drop, the entire global ocean, was assembled from material that came baked inside rocks, delivered piece by piece, collision by collision, over an unimaginable stretch of time. You're not looking at a feature of the planet. You're looking at the accumulated cargo of 1 billion ancient deliveries. Okay, so we've got our delivery driver. We've got the wet asteroids bringing water in, baked into their minerals, arriving late enough to survive. Mystery solved, right? The ocean came from space rocks. Pack it up, go home. But not so fast. Because now the story takes a turn that genuinely sounds like science fiction, and it sent the whole debate sideways. What if not all of Earth's water came from outside? What if a big chunk of it was here all along, hidden, not on the surface, not in the sky, but locked deep inside the planet itself? What if there's an ocean's worth of water buried hundreds of miles beneath your feet, and you'd never know it was there? I know how that sounds. You'd call me crazy, right? An ocean inside the Earth? That's a Jules Verne novel. That's a journey to the center of the Earth. That's not real science. Well, you're not alone in thinking that. But unfortunately for your common sense, you are wrong. And let me explain, because the evidence for this came out of the ground in one of the most ridiculous, lucky, beautiful ways imaginable. It came out of a volcano, riding inside a diamond. Let me set this up properly because the detail here is everything. Diamonds, the ones in jewelry, the ones that cost a fortune. They don't form near the surface. They form deep, really deep. Diamonds form hundreds of miles down, under crushing pressure and intense heat, in a layer of the Earth called the mantle. The mantle is the thick, hot, slowly churning layer of rock between the thin crust we live on and the molten core at the center. It's solid rock, but over millions of years it flows and convects like incredibly slow, incredibly hot taffy. And way down in that mantle, under all that pressure, carbon gets squeezed into diamond. So a diamond is, in a real sense, a messenger from the deep. It's a little time capsule that formed far below the surface, and every now and then, a violent volcanic eruption grabs a batch of these deep diamonds and rockets them up to the surface fast enough that they survive the trip. The diamond is a courier carrying a sealed message up from a place we can never go. And here's the thing about diamonds. They are incredibly tough and incredibly good at sealing things in. Sometimes, when a diamond forms, it traps a tiny speck of the surrounding rock inside itself. A flaw, an inclusion, a little imperfection that a jeweler would hate, but a scientist would absolutely lose their mind over. Because that trapped speck is a perfectly preserved, pressure-sealed sample of the deep mantle, a piece of rock from hundreds of miles down, locked in a diamond vault and carried up to the surface completely unchanged. You cannot drill that deep. No drill on Earth comes anywhere close, but a diamond can bring the sample to you, for free, spat up by a volcano. So back in 2014, same year as the Rosetta result, funny enough, a big year for water, scientists got their hands on one of these diamonds. This one came from Brazil, dug up from a region called Juína, a not particularly pretty little brown diamond, the kind nobody would put in a ring. But inside it was an inclusion, a trapped little speck of mineral, and when they analyzed that speck, they found something that made the whole field sit up straight. The mineral inside that diamond was something called ringwoodite. Ringwoodite is a special form of a very common mineral called olivine, but olivine that's been squeezed into a different crystal structure by the insane pressure of the deep mantle. It only forms at very specific depths, in a zone scientists call the transition zone, roughly 250 to 400 miles down, a boundary layer deep inside the planet. So just finding ringwoodite in a natural sample was a big deal, because it confirmed this stuff actually exists down there the way the theories predicted. But that wasn't the headline. The headline, the thing that made jaws drop, was what the ringwoodite was carrying. The ringwoodite was wet. That tiny crystal, that speck trapped in a brown diamond from Brazil, contained water. Trapped water, locked into its crystal structure, and not a trace amount either. The ringwoodite was something like 1% water by weight. Now 1% might not sound like much, but you have to understand what it implies. And this is the part that breaks your brain. Let me explain. Ringwoodite makes up a huge fraction of that transition zone deep in the mantle. If ringwoodite all through that layer is even partly as wet as this little sample, if that water content is anything close to typical, then the total amount of water locked inside that one deep layer of the planet is staggering. We're talking about potentially as much water hidden inside the Earth as there is in all the oceans on the surface, maybe more. Some estimates say the water trapped in the mantle's transition zone could be equal to all the surface oceans, and the bolder estimates push it to as much as 3 times all the surface oceans combined. Let that detonate in your head for a second. 3 times all the world's oceans, locked in rock, hundreds of miles beneath your feet, an ocean you will never see, never swim in, never sail across, an ocean with no waves and no shore, not a body of liquid water, but water woven into the very crystal structure of the rock, spread through a buried layer roughly 400 miles down. There is, in a very real sense, a hidden sea inside the planet, and we only know it's there because a volcano coughed up a diamond with a wet crumb of evidence sealed inside it. And here's why this turns the whole mystery on its head. If there's that much water buried deep inside the Earth, then maybe the planet wasn't quite as bone dry at birth as we thought. Maybe some of that deep water was incorporated into the planet as it formed, locked away inside minerals deep in the interior where even the Theia impact couldn't fully cook it out, because it was buried too deep and bound too tightly into the rock. The deep mantle could be a kind of vault, a place where original water survived the chaos that scrubbed the surface clean. And over the long, slow life of the planet, water can move between that deep reservoir and the surface, released through volcanoes over hundreds of millions of years, cycled down into the mantle by sinking tectonic plates, and back up again. The inside of the Earth and the oceans on top of it might be in a slow, ancient conversation, trading water back and forth on timescales that make a human lifetime look like a single blink. So now the real picture starts to come together, and it's so much richer than the simple version. The answer to where Earth's water came from probably isn't one source. It's a combination. It's wet asteroids raining in from out past the frost line, delivering water baked into their minerals, arriving late enough to survive after Theia reset the planet. That's the late veneer, the soggy gray rocks doing the heavy lifting. And it's also water that may have been folded deep into the planet's interior from the very beginning, hidden in the mantle, surviving the fire, slowly leaking up and out over billions of years. Maybe a splash of genuine comet water in the mix too, here and there, since a few comets do carry the right kind. The ocean isn't from one delivery, it's from many. The sea is a blend, brewed over billions of years from sources both above and below. And now picture the moment it all came together on the surface, because this is one of the most cinematic scenes in the planet's history, and almost nobody ever thinks about it. Picture this: early Earth, finally cooling down after the Theia chaos, after the magma ocean. The surface is starting to harden into the first crust. The atmosphere is thick and steamy, loaded with water vapor, water that came from the volcanic outgassing of the interior, and from all those wet rocks that hammered in. The whole sky is basically a planet-sized cloud of steam, choking and hot, the air itself swollen with all the water that's going to become the sea. And as the surface cools just enough, that vapor starts to condense, it starts to fall, and it rains. Not a rainstorm, not a season of rain. Picture rain that falls, and keeps falling, and does not stop, not for days, not for years, but for thousands of years. Continuous rain, a global, relentless downpour, draining the steam out of the sky and pouring it onto the bare rock below. Imagine standing on that early Earth. You couldn't, you'd be cooked, but imagine it, under a sky that has been raining without a break since before you were born, and will keep raining long after you're gone. Thousands of years of non-stop rain, filling every low spot, every basin, pooling and rising and spreading until the first oceans are born. The seas didn't appear all at once. They were filled, drop, by the longest rainstorm the planet has ever known. Every ocean you've ever seen started as that endless, ancient rain hammering down on naked stone. And I really want you to feel the absurd, beautiful improbability of all of it. Every single thing had to line up. The planet formed in the dry zone, too hot for water, so by rights it should be a desert. It got smashed by a Mars-sized world that should have sterilized everything. And then, against those odds, water found its way here anyway, smuggled inside asteroids that arrived at exactly the right late moment, possibly hidden in a vault deep in the mantle that survived the fire, and then poured out across the surface in a rainstorm that lasted longer than all of recorded human history, many times over. Any one of those steps going differently, and you've got a dead rock, a Mars, a Mercury, a Venus with its oceans boiled off into a runaway hothouse. Instead, you got the one place we know of with liquid water oceans, the one place with waves, with tides, with life. The whole thing balanced on a knife's edge, and it landed, somehow, on you. And here's where this story stops being about astronomy and becomes about you, personally, in a way you've never thought about. Because that ancient ocean, the one that filled up over thousands of years of rain, made of water smuggled here inside rocks from across the solar system, you're carrying a piece of it around right now, inside your own body, in your blood. Let me explain, because this is the part that gives me chills every time. Your blood is salty. You know this. You've tasted it when you've had a cut, that little metallic, salty tang. There's salt dissolved in your blood, in the fluid that surrounds your cells, in basically all the watery parts of you. And here's the wild thing. The concentration of salt in your blood, the saltiness of the fluid your cells float in, is strikingly close to the saltiness of the ancient ocean. The story goes that life first arose in the early seas, and when our distant ancestors, the first cells, the first creatures, finally crawled out of the water and onto the land, they didn't leave the ocean behind. They couldn't. Their cells had evolved to work bathed in seawater, to live in that exact chemistry. So they took the ocean with them. They sealed a little bit of the sea inside their own bodies and carried it onto dry land, and every generation since has passed that inner ocean down, all the way to you. That's the punchline of this whole impossible saga. The salt concentration in your blood mirrors the ancient ocean. The first sea is still inside you. When you cry, you are literally leaking a tiny droplet of a 4 billion-year-old ocean that was delivered to this planet inside falling rocks and poured out across the world in a rainstorm that lasted longer than civilization. Every heartbeat is pushing that ancient seawater through your veins. You are a walking, talking jar of the primordial sea, sloshing it around inside a skin-covered container, carrying the ocean with you everywhere you go, into the shower, onto the bus, up the stairs, into your bed at night. And that, basically, is the answer to a question that shouldn't even have an answer. Earth's oceans physically shouldn't exist. The planet was born in the dry zone, too close to the sun, then got reset by a planetary collision that should have left it parched forever. And yet here you are, on a 70% water world, with the whole improbable delivery story written in chemistry, in the deuterium barcode that cleared the comets and convicted the asteroids, in the wet crumb of ringwoodite a volcano spat up inside a diamond, in the thousands of years of rain that filled the first seas. The hunt for where the water came from started up in the sky, with dirty snowballs and gray rocks, and it ended in the most personal place imaginable, in the salt of your own blood. The ocean came from somewhere out there, and now a piece of it is in here, in you, and it always will be. Now, I told you the comets got cleared and the asteroids took the rap, but I left out a part of the investigation that genuinely keeps scientists up at night, because the asteroid story has a crack running right through it. And the crack is this. If the wet asteroids delivered Earth's water as a late veneer, raining in after the Theia chaos, then there's a number we should be able to predict. We should be able to figure out roughly how much of that late material smashed into the planet, and roughly how much water it should have carried, and those two numbers should add up to something close to the size of the oceans. Let me explain why that matters, because it's the kind of bookkeeping that makes or breaks an entire theory. Here's how scientists do the accounting. When those wet carbonaceous asteroids hammered into the late Earth, they didn't just bring water, they brought metals. And not the boring metals. They brought what scientists call the highly siderophile elements, which is a mouthful that basically means iron-loving elements. Things like gold, platinum, iridium, osmium. These are metals that love to bond with iron. And here's the key. Early in Earth's history, when the planet was a ball of magma, all the iron sank to the center to form the core, and it dragged every one of these iron-loving metals down with it. Gold, platinum, all of it, plummeted to the core along with the iron, like coins falling to the bottom of a pond. So the rocky outer part of the Earth, the mantle and crust, should have been completely stripped of those metals, scrubbed clean. There should be no gold near the surface at all. But there is. There's gold in the ground. There's platinum. There's iridium. There's all of it, scattered through the mantle and the crust where, by rights, it shouldn't be. So where did it come from? Here's the crazy part. It came from the late veneer. Those same wet asteroids that arrived late, after the core had already formed and locked away the original gold, they came in carrying a fresh load of these iron-loving metals. And because they arrived late, after the core was sealed off, their gold and platinum had nowhere to sink to. It just stayed up near the surface, mixed into the mantle and the crust. Which means, and this is the beautiful part, every piece of gold you've ever seen, the ring on someone's finger, the bars in a vault, the gold in your phone, came from asteroids that smashed into the planet billions of years ago. That gold is alien. It fell out of the sky. And here's why it matters for the water mystery. If you measure how much of this iron-loving metal is sitting in the mantle, you can work backward and figure out roughly how much asteroid material arrived in that late veneer. And then you can ask, okay, if that much wet rock came in, how much water did it bring? And when scientists run that calculation, the answer is, broadly, in the right ballpark. The amount of late material that delivered the gold is roughly consistent with the amount of material you'd need to deliver the oceans. The gold and the water are telling the same story. The wedding ring and the sea are siblings, both delivered by the same fleet of falling rocks. Turns out the thing on your finger and the thing in your bathtub came from the same place, which, when you think about it, is a genuinely insane fact to carry around in your head. But, and the universe always has a but, the bookkeeping doesn't close perfectly. The deuterium fingerprint of Earth's water is a really good match for those carbonaceous asteroids, yeah. But when scientists measure other fingerprints, other isotopes, the picture gets muddier. There are elements like nitrogen and the noble gases, and certain isotopes of hydrogen, where Earth's signature doesn't line up cleanly with any single source. It's like the planet's water has a slightly mixed accent. Mostly it sounds like wet asteroids, but there's a trace of something else in there, an undertone you can't quite place. And that's the clue that sent scientists hunting for a deeper, weirder source. Because if the water isn't purely from late asteroids, then where's the rest of it coming from? Let me explain, because the answer involves the sun itself. Here's an idea that, when I first heard it, made me put my coffee down. What if some of Earth's water was never delivered as water at all? What if it was assembled here, on the planet, out of raw ingredients that came from completely different places? Stay with me. Water is hydrogen and oxygen. Oxygen, the planet had plenty of, baked into the rocks from the start. Rock is full of oxygen bound up in minerals. So you don't need to import oxygen. You only need hydrogen. And hydrogen is the lightest, most common element in the entire universe. So the question becomes, could Earth have grabbed hydrogen from somewhere and just married it to the oxygen already in the rocks to make water on site? And this is where it gets wild. When the solar system was young, before the planets had fully formed, the whole disk was bathed in gas, vast amounts of hydrogen gas, left over from the cloud that formed the sun. And the young Earth, while it was still growing, may have pulled in some of that hydrogen, dissolving it into its magma ocean, soaking it up like a sponge. Then that hydrogen, deep inside the molten planet, could react with oxygen-bearing iron oxides in the rock. And there you go. Make water. Water manufactured in the basement, from imported hydrogen and homegrown oxygen. The planet potentially cooked up some of its own oceans from scratch, using gas it inhaled directly from the cloud that made the sun. That's not delivery. That's the planet brewing its own sea in its guts. And the wild thing is, this so-called nebular hydrogen, the gas from the original cloud, has a much lighter deuterium fingerprint than asteroid water. So if you blend a little of this homemade light water with a lot of asteroid water, you can fine-tune the final fingerprint to match Earth's exactly. The slightly mixed accent of the ocean suddenly makes sense. It's mostly asteroid with a whisper of the original solar cloud stirred in. Now I want to slow down and really sit with the deep Earth water again, because we breezed past it and it deserves more, since it's honestly the strangest character in this whole story. We talked about the ringwoodite in the diamond, the wet crystal from 400 miles down. But I don't think the picture of what that means has fully landed yet, so let me paint it properly. When scientists say there might be an ocean's worth of water, or 2, or 3, locked inside the mantle, your brain immediately pictures a giant cavern of dark water sloshing around in the middle of the Earth. A literal hidden sea, the Jules Verne fantasy, glowing lakes and caverns measureless to man. And I have to take that picture away from you, because the reality is so much stranger than the fantasy. There is no cavern. There is no pool. The water down there isn't liquid, and it isn't ice, and it isn't even really water as you'd recognize it. It's water that has been torn apart and stitched into the rock at the atomic level. Picture this. Hundreds of miles down, the pressure is so monstrous that solid rock behaves in ways that break all your surface intuitions. And in that crushing dark, the water molecules don't get to stay whole and free. Instead, they get pulled apart into their components, and those components, hydrogen and the little water-related groups chemists call hydroxyl, get bonded directly into the crystal lattice of the minerals. The rock literally has water woven into its structure, atom by atom. The mineral and the water become one thing. So if you could somehow teleport down there and grab a fistful of that transition zone rock, it would feel bone dry and hard as anything you've ever touched. It would not be wet. It would not drip. But hidden inside that dry-feeling rock, locked in the lattice, would be water, and a lot of it. The whole layer is a sea pretending to be stone, an ocean disguised as a rock, bone dry to the touch and soaking wet on the inside, all at once. And here's the part that I think is genuinely beautiful, because it ties the inside of the planet to the outside in a slow, living loop. That deep water isn't just sitting there forgotten. It moves. Over hundreds of millions of years, the deep Earth and the surface oceans are trading water back and forth, and the machine that does the trading is plate tectonics, the slow, grinding dance of the giant slabs of crust that make up the surface of the planet. Let me walk you through the loop, because once you see it, you'll never look at the ground the same way. The surface of the Earth is broken into these enormous plates, and they're always moving, inch by inch, slower than your fingernails grow. In some places, two plates collide, and one of them dives down beneath the other, plunging back into the deep mantle. Scientists call this subduction. And here's the thing. When an oceanic plate dives down into the Earth, it doesn't go down dry. It's been sitting under the ocean for millions of years, soaking up seawater, and its rocks have become hydrated, water-bound into their minerals, just like in those wet asteroids. So as that plate sinks, it carries water with it, dragging the ocean down into the planet, hundreds of miles deep, feeding the hidden reservoir. The sea is being swallowed, slowly, perpetually, right now, as you sit there. And then the loop closes, because water also comes back up. Deep in the mantle, as those sinking slabs heat up and the pressure does its work, water gets squeezed out of the rock, and it rises, and it triggers melting, and it feeds the magma that powers volcanoes. So when a volcano erupts and you see that towering plume of steam blasting into the sky, a big part of that steam is water that's coming up from the deep, water that may have been buried for hundreds of millions of years, finally breathing back out into the air and the sea. The planet inhales the ocean through its trenches and exhales it through its volcanoes. It is, in the most literal sense, breathing water, on a timescale so vast that a single breath takes longer than the entire history of complex life. You are living on a planet that is slowly, eternally, drinking its own ocean and spitting it back out. And every drop in the sea today has probably made that round trip, down into the dark and back up into the light, more than once. Let me put a number on how slow and how huge this is, because the scale is the whole point. The amount of water that cycles down into the mantle and back up over the age of the Earth is enormous, potentially enough to fill and empty the oceans many times over across billions of years. The sea you swim in is not a fixed, permanent thing. It's a flow. It's a level in a tank with a slow drain at the bottom and a slow tap at the top. And the level has stayed roughly steady for a very long time, only because the draining and the filling are, more or less, in balance. And here's a thought that should unsettle you a little. If that balance ever tipped, if the planet started swallowing more water than it burped back up, the oceans could, very slowly, over hundreds of millions of years, start to drain away into the rock. Some scientists genuinely think this could be the long-term fate of the planet, billions of years from now. The seas don't have to leave by boiling off into space. They could leave by sinking into the ground, pulled down into the mantle faster than the volcanoes can give them back. The ocean could end not with a roar, but with a slow, silent swallow. But let's come back from the far future, because there's a chapter in the middle of this story I haven't told you yet, and it might be the most important one for why you exist. We've established that water arrived and the oceans filled. But the early Earth, the young planet with its first seas, was a wildly different place from the world you know, and the conditions back then were a kind of miracle balancing act. Here's the thing that should genuinely confuse you. 4 billion years ago, the sun was much dimmer than it is today, much dimmer. The young sun put out something like 70% of the energy it does now, 30% weaker. And here's the problem. If you took today's Earth and dialed the sun down by 30%, the entire planet would freeze solid. The oceans would lock up into ice from pole to pole. It would be a frozen white ball. So with a sun that faint, the early Earth, with its brand new oceans, should have been a frozen wasteland, the water locked up as ice before life ever had a chance. This is a real famous puzzle, and scientists call it the faint young sun paradox. So why didn't the early oceans freeze? You'd think a 30% dimmer sun would have iced the whole place over, and yet the rocks tell us there was liquid water on the early Earth, oceans, even early life, at a time when the sun was far too weak to keep things warm. So what was keeping the young oceans liquid? Let me explain, because the answer is a thick, smothering blanket. The early atmosphere was loaded with greenhouse gases, far more carbon dioxide than today, plus other heat-trapping gases like methane belched out by all that volcanic activity, and later by primitive microbes. That thick blanket of greenhouse gas trapped the feeble sunlight and held the warmth in, keeping the oceans liquid even though the sun itself was nowhere near strong enough to do the job. The planet wrapped itself in a heavy coat and survived a sun too dim to keep it warm any other way. The first seas didn't freeze because the early Earth was running its own private heater, fueled by volcanic gas, exhaling warmth into a sky that held it tight. And you have to appreciate the knife edge here, the same knife edge that runs through this entire story. If that greenhouse blanket had been too thin, the oceans freeze and you get a snowball planet, and maybe life never gets going. If it had been too thick, you get a runaway furnace and the oceans boil and you get something like Venus. Too cold, you're a snowball. Too hot, you're a hothouse. And the early Earth, somehow, threaded that needle, kept its oceans liquid for billions of years through a slow, self-correcting dance between volcanoes pumping out warming gas and rocks and seas pulling it back down. The planet has been balancing on the edge of frozen and boiled for 4 billion years. And the fact that you can dip your toes in the ocean today instead of skating across it or watching it boil is the result of that balance never once failing for long enough to wipe everything out. Which just goes to show how absurdly lucky the ground under your feet really is. And speaking of luck, let me hold the early ocean up against its two neighbors for a second, because the comparison is brutal and it tells you exactly how rare your situation is. Earth had two sister planets that started out, as far as we can tell, with a real shot at oceans of their own: Mars and Venus. Both of them, in the deep past, may have had liquid water on the surface, and both of them lost it in two completely different and equally tragic ways. Look at them, and you're looking at the two doors Earth didn't walk through. Let's take Mars first. Picture this. 3.5, 4 billion years ago, Mars is not the red, dead, frozen desert you know. The evidence carved into its surface tells a different story. There are dried-up riverbeds. There are ancient lake floors. There are deltas, the fan-shaped deposits a river makes where it empties into a standing body of water, the same shape you'd see at the mouth of a river on Earth. There are minerals that only form in the presence of liquid water, clays and salts that need a wet world to exist. The robots we've sent crawling across the Martian surface have driven right up to the shores of vanished lakes and the beds of vanished rivers. Mars, in its youth, had flowing water. It may have had rivers, lakes, maybe even a shallow sea sprawling across its northern lowlands. It was, for a while, a bluish world too, a second water planet, right next door. So what happened? Where did the Martian ocean go? Here's the heartbreak. Mars is small. It's about half the diameter of Earth, much less massive, and that turned out to be a fatal flaw. A small planet has a small core, and it cools down faster, the way a small cup of coffee goes cold faster than a big pot. And as the Martian core cooled, the churning that generates a planet's magnetic field shut down. Mars lost its magnetic shield. And that shield, that invisible magnetic bubble, is what protects a planet's atmosphere from being stripped away by the solar wind, the constant stream of charged particles screaming off the sun. With its shield gone, Mars was naked before the sun, and over hundreds of millions of years, the solar wind peeled the Martian atmosphere away into space, one particle at a time, like wind eroding a sandcastle. As the atmosphere thinned, the pressure dropped, and the warmth leaked away. And the water, it couldn't survive. Some of it froze into the ground as buried ice, locked in the soil and the poles. Some of it escaped to space along with the air. The rivers ran dry, the lakes emptied, the sea evaporated and blew away. And Mars became the silent, rust-colored desert you see today, a planet wearing the dried-up scars of an ocean it lost because it was just a little too small to hold on. Now look the other way, at Venus, and you get the opposite tragedy, the mirror image of the same loss. Venus is almost exactly Earth's size. Same mass, basically, same rock, often called Earth's twin. And Venus is closer to the Sun, but not so close that it had to be doomed from the start. Many scientists think early Venus, for maybe 1 billion years or more, could have had liquid water oceans, mild temperatures, a genuinely habitable surface, a second Earth almost. But Venus took a different road, and it ended in fire. Here's how. Because Venus is closer to the Sun, it ran a little hotter to begin with, and a little hotter means a little more water vapor in the air. And here's the trap, the brutal feedback loop. Water vapor is itself a powerful greenhouse gas. So more heat means more water vapor, and more water vapor traps more heat, and more heat boils off more water vapor, and round it goes, accelerating, feeding on itself. Scientists call this the runaway greenhouse, and it is exactly as catastrophic as it sounds. On Venus, that loop ran all the way to the end. The oceans boiled. Every drop of surface water evaporated into the sky, and once it was up there as vapor, the intense sunlight broke the water molecules apart, and the lightweight hydrogen drifted off into space, gone forever, so the water could never come back. The atmosphere thickened and thickened with carbon dioxide until the pressure at the surface today is more than 90 times Earth's. Standing on Venus would crush you like the deep ocean would. And the temperature climbed to around 900 degrees Fahrenheit, hot enough to melt lead, the hottest planetary surface in the entire solar system, hotter even than Mercury, which sits closer to the Sun. Venus is a furnace wrapped in acid clouds, a planet that drowned in its own greenhouse and then baked the corpse. It had oceans, and it boiled them all away, and now it's the closest thing to hell we've ever found. So there's your lineup. 3 sister worlds, all roughly the same age, all dealt water at the start. Mars, too small, lost its shield and let its ocean freeze and blow away into space, death by cold and emptiness. Venus, too hot, ran a runaway greenhouse and boiled its ocean into the sky, death by fire. And Earth, right in between, not too small, not too close, threading the needle, holding on to its magnetic shield, balancing its greenhouse just right, keeping its ocean liquid for 4 billion years and counting. The only one of the 3 that still has its sea. When astronomers talk about the habitable zone, the so-called Goldilocks zone, the band around a star where it's not too hot and not too cold for liquid water, this is what they mean. Written across 3 worlds you can see in the night sky. Mars is the porridge that went cold. Venus is the porridge that boiled, and Earth is the one bowl that came out just right. And you happen to be born in that bowl, which, statistically, is the kind of luck you really ought to send a thank you card for. Let me come back down to the water itself, the actual oceans, because there's a question buried in all this that I think you've been quietly wondering, and it deserves an answer. We keep saying the water arrived and the seas filled, but why is the sea salty? You taste it, you swim in it, you know it stings your eyes and you can't drink it. But the rain that fell for thousands of years to fill the first oceans, that rain was fresh water. Rain isn't salty, so where did all the salt come from? How did a sea filled by fresh rain turn into the briny ocean you know? Let me explain, because the answer has been happening, slowly, every single day since the first rain fell. The salt comes from the land. When rain falls on rock, it isn't just water. Rainwater is very slightly acidic because it picks up a little carbon dioxide from the air on the way down, and that mild acid, over enormous spans of time, eats away at the rock. It dissolves tiny amounts of minerals out of the stone, including salts, sodium, chloride, all the ingredients of sea salt. And then the rivers carry that dissolved mineral load downhill, washing it off the continents and into the sea. Every river on Earth is, right now, carrying a tiny cargo of dissolved salt down to the ocean. And here's the crucial part. When seawater evaporates back up into the sky to make clouds and rain again, the water leaves, but the salt stays behind. The salt can't evaporate. So over hundreds of millions of years, water keeps cycling in and out, evaporating away and falling as fresh rain. But every cycle, the salt gets left in the sea, accumulating, concentrating, building up. The ocean is salty because it's the place where all the rinse water of every continent finally collects, and the salt has been piling up in it for billions of years with nowhere else to go. The sea is the planet's drain, and the salt is everything the rivers ever scrubbed off the land. Turns out the ocean tastes like the slow, ancient dissolving of entire continents. And now circle that back to the salt in your own blood, because it lands even harder once you understand where the ocean's salt came from. That brine in your veins isn't just an echo of the sea in some vague poetic way. It's an echo of the specific chemistry of an ancient ocean, a sea built from rain that dissolved the early continents and pooled their minerals into the first seas, the exact chemistry that life evolved inside of. When the first cells learn to live, they learn to live in that water, balanced to that saltiness, tuned to that exact mix of sodium and potassium and chloride. And every cell in your body, right now, is still maintaining that ancient balance, still pumping those same ions in and out across its membrane, running a chemistry it inherited from creatures that lived in the sea before there was anything you'd recognize as an animal. Every nerve impulse that fires in your brain, every thought you're having as you listen to me right now, works by shuffling those exact ions, sodium and potassium, back and forth across a membrane, in a salty fluid tuned to the chemistry of a 4 billion-year-old sea. You don't just carry the ocean inside you, you think with it. The first sea isn't a memory in your blood, it's the operating system. Let me pull back out to the scale of the whole planet one more time, because I want you to feel the full weight of what the ocean actually is before we go further. We tend to think of the ocean as the surface, the bit with the waves, the bit you see from the beach. But the ocean is deep, and most of it is a place no sunlight has ever touched. Picture this. You step off a beach and start walking out along the bottom, down the gentle slope of the continental shelf. For a while, it's shallow, sunlit, full of life. Then the floor drops away at the edge of the shelf, and you start descending into the dark. Past a few hundred feet, the red light is gone. Past 1,000, almost all color is gone. The world is blue-black. Past 3,000 feet, you're in total, absolute darkness, a darkness that has never once seen the sun in the entire history of the planet. And you keep going down and down. The average depth of the ocean is over 2 miles, remember. Most of the sea is this cold, black, crushing abyss, and it makes up the largest living space on the planet by far. The sunlit surface you picture when you think of the ocean is just the thin skin on top of a vast, dark world. And in that dark, under pressure that would flatten you instantly, in water near freezing, with no sunlight at all, there is life. Lots of it. Strange, glowing, alien life that we are only just beginning to map. And here's a fact that ties right back into our whole water story in a way I love. At the bottom of the deep sea, in places where the planet's internal heat leaks out through cracks in the crust, there are hydrothermal vents, chimneys of superheated mineral-rich water gushing up from inside the Earth. And around those vents, in total darkness, with no sunlight to power them, entire ecosystems thrive, living off the chemistry of the water and the heat of the planet's interior. Giant tube worms, ghostly crabs, whole gardens of life clustered around hot water bubbling up from the deep. And many scientists now think that places exactly like this, these dark, hot, mineral-rich vents at the bottom of the early ocean, might be where life on Earth first began. Not in a sunny tide pool, not under the open sky, but down in the black, at the boundary between the ocean and the planet's hot interior, right where the water meets the rock. Which means life may have started at the exact seam where the delivered ocean met the deep earth that helped make it. The two halves of our water story, the sky-delivered sea and the planet's inner heat, came together in the dark, and out of that meeting, maybe, came everything. Came the tube worms, came the fish, came the dinosaurs. Came you. And that idea reframes this entire investigation, doesn't it? We started out asking a simple-sounding question: where did Earth's water come from? And we treated it like a detective story, like we were just trying to ID the delivery driver. Comets? No. Asteroids? Mostly yes. A whisper of the original solar cloud? Maybe. A hidden reservoir locked in the deep mantle, breathing in and out over the eons. But the real answer is so much bigger than a single source. The water on this planet is a 4 billion-year collaboration between everything, between the cold rocks that fell from beyond the frost line, and the gas inhaled from the cloud that built the sun, and the deep interior that buried water in its crystal and breathes it back through volcanoes, and the rain that fell for thousands of years, and the rivers that salt the sea by slowly dissolving the continents, and the magnetic shield that kept the air from blowing away, and the greenhouse blanket that kept the whole thing from freezing. Every one of those pieces had to be there. Take any single one away, and you get Mars, or you get Venus, or you get a dead, dry rock orbiting the sun with nobody around to wonder about it. And I keep coming back to the same staggering thought, so let me say it plainly one more time. The default outcome for a planet like Earth was to be dry. Born in the wrong place, too close to the fire, reset by a planetary collision, faced with a dim sun that should have frozen it, and neighbors that show you exactly how a water world dies. The dry, dead path was the easy path, the likely path, the path 2 of the 3 rocky worlds in this neighborhood actually took. And against all of that, water found its way here, stayed here, balanced on the edge here, and pooled into oceans deep enough to hide a mountain range and dark enough to birth life. That is not the boring middle outcome. That is the long shot. That is the planet that by every reasonable expectation shouldn't have any water at all, ending up as the wettest, most alive place we have ever found anywhere. And you're standing on it, drinking it, made of it. 60% of your body, give or take, is water. Water that came from those falling rocks and that breathing mantle and that endless ancient rain. Water that's been cycling through this planet for 4 billion years and is currently, briefly, on loan to you, arranged into the shape of a person who can think about where it all came from. The water in your cells right now was once in a cloud, and before that in the sea, and before that maybe a mile deep in the mantle, and before that, the longest time ago of all, baked into a rock tumbling through the dark between the planets, on its way to a young, hot world that had no business ever becoming blue. And here you are, the temporary, thinking, walking endpoint of that whole impossible journey, which is a lot to carry around in a glass of water. So next time you drink one, maybe give it a second look. It's older than the oceans, older than the continents, older than the planet's first sunrise, and for now, it's yours. Now, I want to take you back even further than we've gone so far, because there's a piece of physical evidence sitting in a lab in Australia that pushes this whole story right back to the beginning of time, and it's smaller than a grain of sand. Picture this. You're in the Jack Hills, a low, dusty range of rust-colored hills in Western Australia, in the middle of nowhere, the kind of place where the heat shimmers off the ground and there's nothing for miles. And buried in the ancient rock, there are tiny, tough little crystals called zircons. Zircon is a mineral that is absurdly durable. It survives erosion, it survives being ground up and re-cemented into new rock, it survives just about everything the planet can throw at it. And because it locks tiny amounts of uranium into its structure when it forms, and that uranium decays at a known rate, scientists can date a single zircon crystal with incredible precision. A zircon is basically a tiny, indestructible stopwatch that started ticking the moment it crystallized. And here's the crazy part. The oldest zircons from the Jack Hills date back about 4.4 billion years. 4.4 billion. Let that sink in, because the Earth itself is only about 4.5 billion years old. These crystals formed within roughly 100 million years of the planet's birth, right in the thick of the chaos, right around the era when Theia hit and the moon formed, and the surface was supposed to be a hellscape of magma. These are the oldest known pieces of the Earth, the oldest physical things we have ever held that are part of this planet. And scientists didn't just date them, they read them. Because the chemistry locked inside a zircon when it forms is a snapshot of the conditions it formed in. And when scientists looked at the chemical fingerprint inside these 4.4 billion-year-old crystals, they found something that rewrote the textbooks. They found signs that these crystals formed in the presence of liquid water. Liquid water. 4.4 billion years ago, on a planet that everybody assumed was still a glowing ball of magma. Let me explain why that's such a bombshell. For a long time, scientists called that earliest chapter of Earth's history the Hadean, named after Hades, the underworld, because the assumption was that it was hell. A surface of molten rock, oceans of lava, constant bombardment, no place for water, no place for anything. But those zircons are whispering a different story. They're saying that within 100 million years of forming, the Earth had already cooled enough, at least in places, to have liquid water on the surface. Which means the oceans may not have waited around for hundreds of millions of years. The water may have arrived and pooled and started forming seas almost shockingly early, while the planet was still basically a newborn. The hellscape cooled down and got wet far faster than anyone thought possible. Those little crystals are basically tiny witnesses, sealed 4 billion years ago, testifying that the sea was already here when the planet was barely out of the cradle. And that early ocean, the one those zircons are hinting at, would have been a place so alien you would not recognize it as Earth at all. So let me put you on the shore of it, because the early ocean was nothing like the blue you picture. Picture this. You're standing on a bare, dark beach of fresh volcanic rock, and there is no sand, not really, because sand is made from eroded rock and shells, and there hasn't been enough time or life to make much of it yet. The sky above you is not blue. It might be orange or brownish, or a hazy, sickly color, because the atmosphere is full of methane and carbon dioxide and other gases, and there is almost no oxygen in it at all. If you tried to breathe it, you'd suffocate. The sea in front of you isn't blue either. The early ocean may have been greenish or murky, tinted by dissolved iron, because there was so much iron dissolved in that water that the oceans were essentially rusty. And the moon, look up at the moon. It's huge. It's enormous in the sky, far closer than it is today, looming over you, because back then the moon orbited much nearer to the Earth. And because it was so close, the tides were monstrous, vast walls of water sweeping in and out, dragging across the rock with a force that no modern tide could match. The days were short too, only a handful of hours long, because the young Earth spun much faster on its axis than it does now. So you'd be standing on this rusty alien shore, under an orange sky, with a giant moon overhead, watching tides like nothing alive has ever seen, while the sun whips across the sky in a day that's over before you'd want it to be. That was the cradle. That was where it all began. And here's a connection that I find genuinely beautiful, tying that giant looming moon right back into the water story. Remember, the moon came from Theia, from the collision that should have sterilized everything. So the same catastrophe that nearly cost the planet its water gave the planet the moon. And the moon, it turns out, may be one of the reasons life had the stability to get going at all. Because the moon, with its gravity, acts like a stabilizer for the Earth's tilt. A planet's axis can wobble over time, and a big wobble means wild, chaotic swings in climate, drastic ice ages, and scorching periods that come and go unpredictably. But the moon's steady gravitational pull keeps Earth's tilt locked in a relatively narrow, stable range, which keeps the climate relatively stable over long timescales, which gives the oceans and the life in them the steady conditions they need to flourish. Without that giant moon holding the planet steady, Earth's climate might have lurched all over the place, freezing and roasting the young oceans in unpredictable cycles. So the very same impact that almost killed the water gave us the moon that helped protect the water made. The worst day in the planet's history was also, somehow, one of the best. Which just goes to show that you can never quite tell in the moment whether a catastrophe is the end of you or the making of you. Now, those giant early tides I mentioned, the ones from the close-up moon, they might be more important to your existence than you'd ever guess. And I want to slow down on this because it's one of those ideas that quietly blows the doors off. Think about what a tide actually does. Twice a day, give or take, the tide comes in and floods an area, and then it goes out and leaves that area exposed. So along the edges of the sea, there's this band of land that is alternately soaked and then dried, soaked and then dried, over and over on a relentless cycle. And on the early Earth, with that giant close moon and those monster tides, this wetting and drying cycle would have been happening across huge stretches of shoreline, intensely, every single short day. And here's why that might matter enormously. Some scientists think these tidal zones, these places that got repeatedly flooded and then dried out, were the perfect natural laboratory for cooking up the chemistry of life. When a little pool of water rich in dissolved chemicals dries out, the chemicals get concentrated, squished together, forced to react. Then the tide floods it again, washes things around, and it dries out again, concentrating things further. Wet, dry, a natural chemistry set, cycling endlessly, mixing and concentrating the building blocks of life over and over until, maybe, something clicked. Until simple molecules linked into more complex ones, and those into the first self-copying chains, and those, eventually, into the first living things. And the engine driving that cycle, the thing flooding and draining those pools, was the tides. And the tides were driven by the moon, which was made by Theia. The collision that should have ended everything may have, through a chain of consequences nobody could have predicted, set up the exact conditions that started life. The fingerprints of that single ancient disaster are on everything: the moon, the tides, the stable climate, maybe life itself. Let me pull on a different thread now, because there's a part of the water story we've only touched, and it's the most consequential thing that ever happened in those oceans, the event that changed the entire planet from the inside out. We've talked about how life may have started at the vents or in the tidal pools, but for a very, very long time after life began, the Earth's oceans and atmosphere had almost no free oxygen in them. None of the oxygen you're breathing right now. The early world was a world without breathable air. And then, somewhere in the ancient sea, a tiny organism worked out a trick that would remake the world. Let me explain, because this is one of the great turning points in the history of the planet. The organisms were cyanobacteria, tiny, single-celled microbes living in the early oceans, and they invented, or stumbled into, photosynthesis. The kind of photosynthesis that takes in sunlight and water and carbon dioxide and produces energy, and as a waste product, spits out oxygen. At first it didn't change much, because the oxygen they produced got soaked up immediately. Remember all that dissolved iron in the early oceans? The fresh oxygen reacted with that iron and turned it into rust, which settled to the seafloor in vast layers. We can still read those layers in the rock today, these striped formations called banded iron formations, mile upon mile of ancient rusted ocean, basically the receipt for the oxygen that got produced and immediately swallowed by the sea. The early ocean rusted out before the air ever got a chance to fill with oxygen. But the cyanobacteria kept multiplying, kept pumping out oxygen for hundreds of millions of years, and eventually the iron ran out. The sea couldn't soak up anymore, and the oxygen started building up, first in the water, then bubbling out into the sky. And here's the crazy part. This was a catastrophe. We call it the Great Oxygenation Event, and from the point of view of the life that existed at the time, it was an apocalypse. Because for all those early organisms, oxygen was poison. It was a toxic, corrosive gas that their chemistry couldn't handle. So when the oceans and the air filled with oxygen, it triggered what may have been the biggest mass extinction in the history of the planet, a die-off of the very life that had ruled the early seas. The microbes that made the oxygen basically poisoned their own world and wiped out most of their neighbors. It's sometimes called the oxygen catastrophe, and it's a brutal little irony. The single most important thing that ever happened for complex life, the filling of the world with breathable oxygen, started as a planet-wide poisoning. And here's the twist that brings it home. That oxygen, the oxygen that catastrophe pumped into the world, is the oxygen you are breathing right now. Every breath you take, every lungful of air, is a gift from those ancient microbes in the early ocean, the ones that rusted the sea and then poisoned the sky and accidentally made the planet breathable for everything that came after. The air in your lungs is ocean exhaust, 4 billion years old. The sea didn't just give you the water in your blood. It gave you the breath in your chest. And that's the thing I keep wanting to hammer home about these oceans. They're not a backdrop. They're not the stage that life performs on. They are the engine. They made the air. They harbor the chemistry. They run the climate. Let me show you that last part, the climate one, because it's the most active and the most underappreciated job the ocean does. And it's happening right now, every second, holding your whole world steady. The ocean is the planet's great heat engine and its great thermostat. Here's how. The sun heats the tropics far more than the poles, so you'd expect the equator to be unbearably hot, and the poles to be frozen solid, and the middle to be a chaotic mess. But the ocean smooths it all out. Warm water from the tropics flows toward the poles in vast currents, carrying heat with it, and cold water flows back toward the equator, in a planet-spanning system of currents that move heat around the globe like a circulatory system. There's a great conveyor belt of water, scientists call it the thermohaline circulation, that loops through all the oceans, sinking in the cold polar seas where the water gets dense and salty, creeping along the bottom for centuries, and rising again elsewhere, a single, slow, connected loop that takes around 1,000 years to complete one full circuit. 1,000 years for one lap. The water moving past you at the beach might not see that same spot again for a millennium. And that conveyor belt is one of the main reasons the planet's climate is mild enough, stable enough, evenly enough heated for life to spread across it. The ocean is moving heat from where there's too much to where there's too little, constantly, ceaselessly, and it has been doing this for billions of years. The sea is the reason the planet doesn't have a scorching, lifeless equator and a frozen, lifeless everywhere else. And the ocean does something even bigger than moving heat. It stores it, and it stores carbon, on a scale that dwarfs everything else. The ocean holds vastly more heat than the atmosphere does. The top few feet of the ocean alone hold about as much heat as the entire atmosphere above it. And it has absorbed an enormous amount of the extra heat that's been building up on the planet, soaking it up, buffering the whole system, slowing changes that would otherwise come much faster and harder. The ocean is the planet's shock absorber. It takes the blows so the air doesn't have to take them all at once. And it does the same thing with carbon dioxide. The ocean absorbs a huge fraction of the carbon dioxide that enters the air, pulling it down into the water, locking it into the deep, into shells, into the sediment on the sea floor. Over the long, long history of the planet, this slow swallowing of carbon by the ocean has been one of the main controls on the climate, one of the dials that's kept Earth out of the snowball and away from the runaway furnace that cooked Venus. The sea has been quietly running the planet's thermostat the entire time, and most people walk past it on a beach and see nothing but waves. Now here's something that should genuinely stop you in your tracks when you put it next to everything we've covered. With all of that, the ocean making the air, running the climate, storing the heat and the carbon, birthing the life, with all of that going on, we have explored almost none of it. Let me give you the number because it's embarrassing in the best way. We have mapped in detail only a tiny fraction of the ocean floor. The vast majority of the sea bottom, the largest landscape on the entire planet, has never been seen by human eyes or mapped in any real detail. We have better, more complete maps of the surface of the Moon and of Mars than we do of the floor of our own ocean. Sit with that. We can point a telescope at Mars and map its mountains and canyons in fine detail from millions of miles away, but the bottom of the sea that covers most of our own world is, to a staggering degree, a blank. Because water is hard to see through. Light doesn't go far down there, and radio and the tools we use to map other worlds from space can't pierce miles of seawater. To map the seafloor, you basically have to go there, with ships and sonar, dragging across the surface inch by inch, and the ocean is just so vast that we've barely scratched it. The biggest unexplored frontier on Earth isn't some distant mountain range or jungle. It's right below the waves, most of it, in the dark, unmapped and unseen. And in that unmapped dark, we keep finding things that don't make sense. We've found mountain ranges under the sea that dwarf anything on land. The longest mountain range on the planet isn't the Andes or the Himalayas, it's the Mid-Ocean Ridge, a chain of underwater mountains that snakes around the entire globe for tens of thousands of miles, almost all of it hidden beneath the waves, a planet-circling spine of rock that almost no human will ever lay eyes on. We found the deepest place on Earth, the Mariana Trench, plunging down nearly 7 miles, deep enough that if you dropped Mount Everest into it, the peak would still be more than a mile underwater. We found creatures down in that crushing dark that look like they came from another planet. Fish with their own headlights, animals that glow, things that have never seen the sun and never will. We found whole ecosystems, like those vent communities, running on chemistry instead of sunlight, rewriting what we thought life even needed to exist. And every expedition that goes down brings back new species, new landscapes, new mysteries. The ocean is not a solved place. It's barely an opened place. The water that came here from falling rocks and breathing mantle and ancient rain is still keeping most of its secrets. Let me bring it back around to the question that started all of this, because I think we can finally see the full shape of the answer, and it's stranger and grander than the simple version we started with. We asked where Earth's water came from, and we treated it like a whodunit, and the suspects all turned out to be partly guilty. The wet asteroids did most of it, smuggling water inside their rocks across the frost line and arriving late enough to survive the fire. And we know it was them because the deuterium fingerprint matches, and the alien gold they delivered shows up in the bookkeeping. A whisper of the original solar cloud, inhaled into the magma and married to the planet's own oxygen, fine-tuned the recipe. And a deep, hidden reservoir locked in the mantle, breathing in and out through trenches and volcanoes over hundreds of millions of years, has been quietly cycling water between the inside and the outside of the planet the whole time. The ocean isn't from one place. It's a 4-billion-year-old blend, assembled from the sky and the rock and the deep, poured out in a rainstorm that lasted longer than civilization, salted by the slow dissolving of the continents, kept liquid by a greenhouse blanket and a magnetic shield and a giant stabilizing moon, and so far never once lost to the cold of space like Mars, or boiled into the sky like Venus. And the more you understand about how it got here, the more absurd it becomes that it's here at all. Every step was a coin flip that came up the right way. Form in the dry zone, but get the water delivered late. Get smashed by a planet, but have that smash make a moon that stabilizes your climate and drives the tides that may have started life. Face a dim young sun, but wrap yourself in exactly enough greenhouse gas to stay liquid without boiling. Have neighbors on both sides show you precisely how a water world dies, by freezing and by burning, and walk between those two fates for 4 billion years without slipping. Any one of those going the other way, and there's no ocean, no air, no life, no you. The whole thing is a tower of improbable luck, balanced one piece on top of another, and you're sitting on the very top of it, breathing the air an ancient catastrophe made, your blood salted like a sea that fell from the sky, your every thought firing in a fluid tuned to a 4 billion-year-old ocean. So here's where I want to leave this part of the story, with a thought I keep turning over. When you look at the ocean, really look at it, from a cliff or a beach or an airplane window, that vast, restless blue going all the way to the horizon, you are not looking at a feature of the planet. You're looking at a visitor. You're looking at the accumulated cargo of 1 billion ancient deliveries, water that crossed the solar system inside rocks to get to a world that, by all rights, should have been a desert. You're looking at the place life began, the engine that made the air, the thermostat that holds the climate steady, the largest unexplored wilderness on Earth, and the chemical ancestor of the salty fluid in your own veins, all at once, all in that one moving sheet of blue. The ocean shouldn't be here, and it is, and so are you. And the two of those facts, it turns out, are the same fact, written at different scales, one across an entire planet, and one inside a single beating heart. Okay, so before we close the book on this, I want to chase down a few loose threads that have been nagging at me, because the water story has these strange little tributaries that lead to places you'd never expect. And the first one is this. We've been treating Earth like the lucky winner, the one bowl of porridge that came out just right. But here's a question that flips the whole thing around. If water arrived here from rocks tumbling across the solar system, and if water turns out to be locked inside asteroids all over the place, and if there might be oceans hidden inside rock the way there's one hidden inside our own mantle, then is Earth actually special at all? Or is water everywhere, and we just happen to be the spot where it pooled on the surface where you can see it? Let me explain, because the answer is genuinely unsettling in the best possible way. When we started looking around the solar system with this water question in mind, we found water absolutely everywhere we looked. Not in the form you'd recognize, not blue seas under a sky, but water, all over the place, hiding. There's water ice at the poles of the moon, tucked into the floors of craters that never see sunlight, frozen for billions of years in the dark. There's water ice on Mars, locked into the soil and stacked at the poles, the frozen remains of those rivers and lakes Mars lost. There's water frozen into comets and asteroids by the trillion, drifting out in the cold beyond the frost line. But here's where it gets truly wild. The biggest oceans in the entire solar system might not be on Earth at all. They might be out past the asteroid belt, on moons you've barely heard of, hidden under shells of ice. Picture this. You travel out to Jupiter, and you find a moon called Europa. It's a little smaller than our own moon, and from the outside it looks like a smooth, cracked ball of ice, crisscrossed with reddish lines like a giant frozen marble. But underneath that ice shell, scientists are now almost certain there is an ocean. A real, liquid, saltwater ocean sloshing around under miles of ice. And here's the crazy part. That hidden ocean on Europa may contain 2 or 3 times as much liquid water as all of Earth's oceans put together. Twice the water of our entire planet, on a moon you could fit inside our own. And it's not alone. Out at Saturn, there's a little moon called Enceladus. Tiny, barely 300 miles across, and it has a hidden ocean too. And we know because we've actually seen it. There are cracks near the south pole of Enceladus, and out of those cracks, giant geysers of water are blasting straight up into space, plumes of seawater erupting off the surface and freezing into a spray of crystals. A spacecraft called Cassini flew right through those plumes and tasted them, flew through the spray of an alien ocean and analyzed it, and found water, salt, and the kind of organic chemistry that, on Earth, we associate with the building blocks of life. There's another moon of Saturn, Titan, with lakes and rivers on its surface, though those are made of liquid methane, not water, under an orange smoggy sky, and an ocean of water hidden deep underneath even that. So think about what that means. The solar system isn't a few dry rocks and one wet Earth. The solar system is soaking, It's dripping with hidden oceans, frozen seas, buried water, plumes of brine erupting into space. Water, it turns out, is one of the most common things in the universe. Hydrogen is the most abundant element of all, and oxygen is right up near the top, and the two of them find each other constantly, all across the cosmos, in clouds between the stars, in the disks where planets form, in the bones of asteroids and comets and moons. Which means Earth's water isn't a fluke of chemistry. Water is everywhere. What's rare, what's genuinely special about Earth, isn't that it has water. It's that it has water on the surface, liquid, under an open sky, warmed by a sun at just the right distance, kept liquid by just the right air for billions of uninterrupted years. The miracle isn't the water. The miracle is the shoreline. The miracle is the rain falling on bare rock and pooling into a sea you can stand beside and feel the wind off of. Most of the water in the solar system is locked in the dark, under ice, inside rock, hidden. Earth is the rare place where the water came out into the light, and that reframes the search for life beyond Earth in a way I find genuinely thrilling. Because if life on our planet may have started at the seam where the ocean met the planet's hot interior, down at those dark vents on the seafloor, then every one of those hidden moon oceans, sloshing in the dark against a rocky core, warmed by the squeeze and pull of a giant planet's gravity, is a place where the exact same thing could be happening right now. Europa has a rocky floor under its hidden sea, and where rock meets water and heat, you might get vents, and where you get vents, you might get the same chemistry that may have kindled life here. When we send probes to drill through the ice of Europa or to fly back through the geysers of Enceladus, and we are planning to, missions are already on their way and being built. We're not just looking for water. We know the water's there. We're looking to see whether the water did, somewhere else, the same impossible thing it did here. Whether the story we've been telling this whole time, the story of water finding rock and heat in the dark and waking up into life, happened more than once. And if it happened on a moon of Jupiter, on a moon of Saturn, in our own backyard, then it almost certainly happened a billion times over, out among the stars. The water story might be the most common story in the universe. We just don't know yet whether we're the only ones reading it. Let me bring it back home, though, because there's one more thread I have to pull, and it's the most personal one of all, and it closes the loop on everything. We've talked about the salt in your blood echoing the ancient sea, but I want to go further than that, because the connection between you and that water is even more total than a chemical echo. Here's the thing. Before you were born, before you took a single breath of that ancient ocean-made air, you spent 9 months floating in water. You were suspended in fluid in the womb, weightless, surrounded by warm liquid, the way your distant ancestors floated in the early sea. And the chemistry of that fluid, the salty mineral balance of it, is, once again, a close match for seawater. You began your life the same way life itself began, floating in a tiny private ocean, before you ever met the air. Every single person who has ever lived spent their first chapter underwater, in a little inner sea, before crawling out into the world, the way the first creatures crawled out of the seas onto the land. We all repeat the oldest journey on the planet, every one of us, before we're even born. The sea isn't something you visit on holiday. It's where you came from, twice over, once across 4 billion years of evolution, and once across 9 months in the dark. You are a creature of the water, all the way down. And that water, the water in you, the water in the womb you came from, the water in the sea and the sky and the rivers, it's the same water. That's the part people miss. It's not like the planet keeps making new water. The water that's here is, more or less, the water that's been here, cycling around, used and reused, for billions of years. The water you drank this morning has been everywhere. It has been in clouds and rivers and glaciers. It has been in the ocean and deep in the mantle and frozen at the poles. It has passed through dinosaurs and trees and the bodies of every creature that ever lived and drank and breathed. The water in your glass is the same water that fell as that endless ancient rain, the same water that crossed the solar system inside a tumbling rock, the same water that those first cells floated in at the bottom of the early sea. You are not drinking new water. You are borrowing, for a moment, a few molecules of the most well-traveled, most ancient, most reused substance on the planet, and then you'll give it back, and it'll go on without you, into the next cloud, the next river, the next living thing. You're just one stop on a journey that started before the continents existed and will keep going long after you're gone. And I think that's the thought I want to leave you with, because it changes how the whole thing feels. We started this asking a sort of cold, technical question. Where did Earth's water come from? And we ran it down like a detective story, ruling out the comets, fingering the wet asteroids, uncovering the hidden ocean in the mantle, tracing the late veneer by the alien gold it left behind, watching the rain fall for thousands of years to fill the first seas. And every answer was fascinating on its own. But the real answer, the one that actually matters, isn't a fact about asteroids or deuterium ratios. The real answer is that the water came from out there, from the cold dark between the planets, against odds that should have left this world a desert, and it ended up in here. In the ocean you can stand beside, in the air you breathe, in the womb you came from, in the blood that's moving through you right now, salted like a sea that fell out of the sky 4 billion years ago. The oceans physically shouldn't exist. The planet formed in the dry zone, too close to the sun for water to survive. It got reset by a collision that should have sterilized everything. It faced a sun too dim to keep it warm, and neighbors that show you exactly how a water world dies. And against all of that, the water found its way here, and stayed, and pooled, and woke up into life, and eventually arranged itself into something that could look up at the sea and the sky and wonder where it all came from. That something is you. The ocean took 4 billion years and a billion lucky breaks to make a creature that could ask the question. And the answer to the question is, in the end, sitting right there in your own veins, in the salt of your own blood, in the water you'll drink later today without thinking twice about it. So next time you're near the sea, or even just standing at the sink filling a glass, take a second. That water is older than the mountains. It's older than the continents. It's older than the oldest thing you can name. It crossed the void to get here. It built the air and ran the climate and birthed the life that became you. And for a little while, a few molecules of it are yours, borrowed, on loan, passing through, before they move on to wherever water goes next. You are a brief, thinking, walking arrangement of the oldest ocean in the world, and so is everyone you love, and so is every living thing that has ever drawn breath on this impossible blue planet. The sea is inside all of us. It always has been, and honestly, once you really feel that, a glass of water never quite looks the same again. That's the story of where Earth's water came from the dry zone to the wet asteroids, to the ocean hidden in the rock, to the sea in your own blood. Thanks for hanging out and letting me pour all this into your brain. Stay curious, drink your water, look at the sea a little differently, and I'll catch you in the next one.